So I wanted to welcome you to our first class, mathematics class online. But actually, as you're seeing this, we're going to start here from the beginning. So we're actually going to cover also everything we covered in lectures before. Okay, and we're going to start the same way with basics. So the first thing we're going to do is classification of numbers. So we're gonna name each main subset of numbers, so we are sure that we know all proper names and we know how to divide numbers. Okay, so if we have numbers like starting from 1 to 2 to 3 and so forth, we call those natural numbers. Now, if I'm going to take this set of numbers and I'm going to add one more element, we're going to have whole numbers. Then I can extend this set even more, also by adding discrete numbers. What this means you will learn a little bit later. But now going in the opposite direction. So we start from somewhere in negative infinity, but we got numbers like -3, -2, -1, 0, 1, 2, 3. Those numbers we're going to call integers. Okay, so look, what have we covered? If we would have some axes of numbers, then we've got 0, 1, 2, 3, -1, -2, -3, and so forth. But what are we missing? Of course, we are missing everything in between the integers. So what should we add now? The next group we're going to add is called rational numbers. Look, rational numbers, well, name comes, we can conclude what are rational numbers from the root of the word rational, which is ratio. And look, rational numbers are numbers that can be expressed as ratios of two integers. And look, so we can take any two integers with one, of course, restriction that we will never divide by 0, and we can build a fraction of it. So in other words, a ratio. So we will have here a number 1/2, 3/2, -5/2, and so forth. Of course, integers are also rational numbers because each integer can be expressed as a ratio of some other integers. Even 0, because 0 divided by 1, 0, by 2, 0. Okay, so now what we started to do is that we started filling all the places over here. So, but as it turns out, there is still some spaces here left that we haven't filled with rational numbers. Because as it turns out, I hope you remember this also from high school, that not all numbers can be expressed in form of ratios. If they can't, we call them irrational numbers. Okay, what is the example of a number like that? Well, the easiest would be square root of 2, square root of 3, but of course there are some more members of this family, and I want to discuss two of them in extreme detail. The first one is pi. Well, I hope you all remember that pi is approximately 3.14. Now, the more important question is what is pi? And the best way to explain it is, of course, to refer it to a circle. So let's imagine that this is a perfect circle. And let's see, what do we have in this circle? The line from the middle to the side we call radius. The line going through the middle and connecting two points on the circle we call diameter. And finally, the line going around the circle is called circumference. Now, how do we obtain pi? Well, the Greeks found out that if you take any circle and you measure its circumference, then you divide it by diameter of the circle. This is how much you will get, pi. So approximately 314, but of course this number cannot be expressed as a ratio, so it goes so it goes until infinity. But of course this is its meaning, and this is how we obtain it. And as you will see, we will use it also quite often in different economic applications. Okay, the next number that is extremely important for economics is called E. E is approximately 2.72. But what is E? Well, this question is a little bit more complex, but we can explain it very easily using an economic example. Okay, so imagine a situation like this. You've got $1. Interest rate in a bank is 100%. Of course, 100% is a total, so I can simply write it as 1. And now look, imagine that the capitalization of interest, so the time after which bank adds up interest to your account is 1 year. How much money will we have at the end of the year? Well, this question is not very problematic. It's just $2. But how do we get this output? Look, first, let's just denote the amount of money we will have after a year by V. So, this will be $1. Now, if I put money into a bank, I will still receive my original dollar, right? Plus, we need to add the interest to it. The interest is 100%. So, of course, after a year, we've got $2. Okay, now, let's just say the situation changes slightly. We still have $1, but now we have interest rate, half a year interest rate. So after half a year, you are getting additional 50%. Or in other words, 1/2. But also in this scenario, we will have two capitalizations. How much money will we have at the end of the year now? Well, definitely not $2. We will have more. How to calculate it? Well, again, So look, after half a year, we will have $1.50. And now look, over the next half a year, we will get some additional money. But first, of course, we're gonna retain this $1.5, but we're also gonna have additional 50% out of this $1.5. So look, in other words, I could simplify it. I could simplify this and write it as $1 times 1 plus 1 over 2 to the power of 2, which gives us $2.25, which clearly shows us that this is a better option. Okay, so let's go one step further. What if we would have $1, quarterly interest rate would be 25% or 1 over 4, and we would have 4 capitalizations. Well, at this moment, I hope you figured out the formula, how we can calculate it. All I have to do is to take my $1, multiply it by 1 plus 1 over 4, and of course then repeatedly multiply it by 1 plus 1 over 4 3 more times. So we've got 4 over here, and this gives us approximately $2.44. Okay, but let's go even deeper. Let's just say that now we still have $1, but interest rate has fallen to 1 over 12, right? It's approximately 8.3%. And we have, this is monthly interest rate, and we have 12 capitalizations. How much money will we have at the end of the year? Well, we will have 1 times 1 plus 1 over 12 to the power of 12, or approximately $2.61. Okay, well, let me just erase this. We already know the formula, so we'll just keep it this way. Okay, and I hope you can actually see what is going on over there, but let's move further. Look, what now if we still have $1, but interest rate is, daily interest rate is 1 over 365 days, 1 over 365, and we have 365 capitalizations. So, how much money will we have at the end of the year? We will have $1 times 1 plus 1 over 365 to the power of 365, which is approximately 271.5 dollars. Okay, and now let's go further. Let's just now say we have $1 interest rate is based is calculated on the hourly basis. So we've got 1 over 8,760. This is the amount of hours in a year, assuming, of course, you have 36 days. And then we have capitalism. So we in turn have 8,760 capitalizations. At the end of the year, we will have approximately $2.718. So look, what has been happening here? In each consecutive example, our interest rate was declining. But at the same time, number of capitalizations was increasing. And look, here we saw that each time when we reduce interest rate and at the same time increase the number of capitalizations, the amount of money we have has been increasing. But look, it's at the beginning it was increasing 25 cents, then additional 19 cents. Then we had additional 17 cents, and then additional, let's just say 10 cents. And here, the changes we see actually in a space where we don't even have cents. So we have decimal space after a cent. And look where all those numbers are going. They are getting bigger and bigger and bigger and bigger, but they are increasing at slower and slower and slower pace. And as you can guess, I hope at this moment, this number is somehow related to this number. And actually, this is the key. What is key? If I'm going to take a limit, look, limit is telling us, we will be discussing it in details in the future, but limit basically tells us where the value of the function is going as argument of this function is approaching some number. So in our case, let's just say we've got some n approaching infinity out of this expression, 1 plus 1 over n to the power of n. And if we would calculate it, we would get that this is exactly equal to E. So E is how much out of $1 put in the bank you would have if the interest rate was infinitely small, but capitalizations would be taking place every single moment. Actually, more often than nanoseconds. But this we cannot get in this situation more than $2.72. Okay, so now that we covered the E number, we are ready to combine those two sets. Because look, first thing we've done is that we had integers. Then we started filling the places with integers using rational numbers, generally fractions, and of course we couldn't fill every single place in between integers with just those numbers, so we also needed to use irrational numbers. Now we've covered all the places. Now if I'm going to now take rational numbers and irrational numbers, add them all up, I'm going to get real numbers. Now, look, why do we call real numbers real? Because in some or other form, they appear in reality. What do I mean by that? Well, look, you can, natural numbers, you can calculate fingers. Right? 1, 2, 3, 4, 5. Of course, you can calculate other person's fingers as well to get to the big numbers. Now, if you cover all the fingers, you've got 0 fingers. Now, when do we see negative numbers? Well, look, if you have an elevator in a building and the elevator is going above the ground and below the ground, you can think of positive numbers as going up in the building, while negative numbers going to the floors below the building. Then, what about rational numbers? Well, here we need to add some fractions, so look, those are simply parts of other things. Now, irrational numbers, can we see them? Look, of course, we can have a side we can have something that has length square root of 2, square root of 3. We already seen that actually pi is associated with circle. Those are all the numbers that somewhere in the reality we can see basically with negative I. But sometimes, as it appears, we need to use some numbers that do not really exist. In this case, we are using a set of numbers called imaginary numbers. So, what are those imaginary numbers? Well, look, situation here is pretty straightforward. Let's just say that I would tell you to calculate this. You should, after everything you learned from high school, you should say, no, we cannot do it. This has no solution. Because 3 times 3 gives us 9. Negative 3 times negative 3 gives us 9. So it's impossible to get a number that if I multiply by the same number, I will receive negative 9. But as it turns out, there are some problems in which we actually need to calculate square roots out of negative numbers. In order to do it, we use imaginary numbers. But actually, there is only one imaginary number. Well, imaginary number is this. Square root of negative 1. What does it mean? Like, look, we have not calculated how much is e. We don't know. All we know is that we've defined that I is square root of negative 1. Now, why do we need just square root of negative 1? Well, look, this is pretty easy. I can easily rewrite negative 9 as 3 times 3 times negative 1, right? I can write this as 3 times 3 times square root of negative 1, which gives me at the end 3 times I. So look, any square root out of a negative number can be expressed in some form with I. Okay, so now look, imaginary number I does not exist, right? So actually, in order to put it into some use in reality, we need to take imaginary numbers, combine them with some real numbers, and then we are arriving at the final set called complex numbers. Look, those complex numbers are usually written in the form that we have some h, where h is a real number, plus minus vi. And look, we simply call that this part is a real part of a number, and this is an imaginary part. And look, of course, this we're going to be discussing in the future. But with this whole thing, we've actually completed classification of numbers. Okay, see you in the next video.